Hello there, geometers. This is a video for, obviously, geometry. It is chapter 4, section 6, and we are looking at isosceles and equilateral triangles today. And before we go further, I just wanted to give you some anatomy of isosceles triangles. And I do this every year because I feel like sometimes students see it seems pretty basic. You have a triangle, there's a base, there's legs. And sometimes when students see the base, they assume that it's at the bottom of the triangle. I just wanted to put two examples up here to make sure that you understand that the triangle can be rotated and stuff. And sometimes the base is not the bottom of the triangle. And it's hard to see that sometimes. So I want to show you a way that you can always know where the base of the triangle is. So basically, in an isosceles triangle, we know that it's isosceles when two of the sides of the triangle are congruent. So we refer to the two congruent sides as the legs. So as a vocab or definition for you, the legs of the isosceles triangle are basically the two congruent sides. So this is not the legs because this side is not marked congruent. Okay? Also you have, so once you've identified where the legs are, then the only side left is the base side. So like over here, you can see that the two legs that are marked congruent are these two, and hence this is not the base. These are the legs, and then this becomes the base because it's the only side that's left. All right? So then of course we have what we call base angles, and the base angles are the two angles that kind of sandwich the base in the middle. So those are your two congruent angles. And then you have, once you've identified the base angles, the only angle left is the vertex angle. We call this the vertex angle of the triangle. So those are all of your pieces. We've got legs, base angles, and vertex angle. And again, this is the same thing, but the triangle here is a little bit rotated. So your vertex angle is down here, and your base angles are here. So there you go. Also, we want to talk to you about the actual isosceles triangle theorem. And it states, and you probably already knew this, but now we have it officially in our lesson. If two sides of a triangle are congruent, then the angles that are opposite those sides are congruent. And the angles that are opposite those sides are basically the angles that we consider the base angles in our diagram earlier. So the base angles, again, we identified that these are the congruent sides. So that means that AB is the base. So the base angles are angle 1 and angle 2 in this case. And so those would be congruent. And it says here, just in case you want a diagram to show, if segment AC is congruent to segment BC, then angle 2 is congruent to angle 1 because they're the base angles. And that's the isosceles triangle theorem. And then we also have it in the converse form. So in this case, you have two sides congruent, base angles congruent. And here we're going to go backwards. If two angles of a triangle, which we'll call the base angles, are congruent, then the sides opposite those angles, which are the legs, are congruent. So we have the theorem and we have the converse of the theorem. So here we have, again, symbolically, if angle 1 is congruent to angle 2, then segment FE is congruent to segment DE, which are the legs of the triangle. So hopefully that all makes sense, and we are going to use that for this example here. It says in part A, name two unmarked congruent angles. So we can see that these are already marked, so we don't want to use those. But to name two unmarked congruent angles, we can see that in this smaller triangle ABC here, we have two legs that are congruent. So we can say that these base angles are congruent. So to name two unmarked congruent angles, we will have to call, we can't call this angle C because it's got two angles there. So this angle can be BCA. So we'll say angle BCA. And also angle B. It's okay to call this angle B because there's no other angle there. And so there you go. And then in part B it says name two unmarked congruent segments. And so we already have that these are marked congruent. So to name two segments that are also congruent, we're going to go with, if these two base angles are congruent, then AC should be congruent to AD. So we're going to go with AD and AC. Those are, now and I don't want this to confuse you. This is marked congruent, but it's marked congruent to that one. So now we want two segments that are congruent to each other that weren't previously marked. So now we're going to use these two. Alrighty, so that's basically how you do that example. And so now we're going to ask you to try one on your own with a different diagram, same instructions. All right, and then we're going to go to an equilateral triangle. In an equilateral triangle, we have two corollaries. And again, if you've forgotten, a corollary is basically a theorem that directly follows from a previous theorem. So we get these two corollaries from the actual theorem of an isosceles triangle. We just add one more step, and then we get these two corollaries. So I just kind of wanted to give you, this diagram goes for the first corollary, and the second diagram goes for the second corollary. So the first corollary says a triangle is equilateral if and only if it is equiangular. And so at this point, you're probably seeing a new symbol, if you will. No, I did not forget how to spell the word if. That is actually a symbol. It's basically an I and then two F's, and those F's are kind of like longer than a normal F. Like here's my normal F, and there's two of them. It's like a if. You don't say if. Okay, that's not how you pronounce that. It basically stands for if and only if. If and only if. And if and only if is a statement that we use, a phrase that we use when the statement can be read forward and backward. So it's an if-then. So you say, if you are a triangle, or if a triangle is equilateral, then the triangle is equiangular. And you can also say, if the triangle is equiangular, then it is equilateral. So it works both ways. We call that a biconditional. And so when that happens, you can make it easier. Instead of writing two sentences, you can say if and only if and make it shorter. And then instead of writing out the whole if and only if, you can abbreviate it with just IFF. So there's the first corollary. And so we have here a diagram. And we've got angle A is congruent to angle B, which is in turn congruent to angle C. So they're all congruent to each other. Then segment AB is congruent to segment BC and also segment AC. There's that guy. Your second corollary says each angle of an equilateral triangle measures 60 degrees. And I hope that makes sense, because we already know from before that the angles in a triangle have to add up to 180. And if they're all going to be the same, all you have to do is take 180 divided by 3, and you'll get 60. So that should be a pretty simple concept there, or theorem. But again, we have if DE is congruent to EF, which is in turn congruent to FE, so all your segments here are marked congruent, then basically the measurement of angle A is the same as the measurement of angle B. And that shouldn't even say that, because we don't even have those letters. It should say the measurement of angle D is equal to the measurement of angle E, which is equal to the measurement of angle F, which would be 60 degrees. So all the angles in an equilateral triangle have to be 60 degrees. So there's that little guy, and we're going to use some of that information to come over here. This is the do-it-yourself one, so I'm going to come on this side, and we're going to answer these little guys over here. It says, find each measure. So in part A, it wants me to find the measurement of angle Y. And so here's angle Y. And so what I'm going to do is I'm going to basically determine that this is actually a equilateral triangle. Okay? And right now, all we know currently is that this is definitely isosceles, because we have the two legs here both labeled 8 inches. So those are the legs, and they're the same, so it's an isosceles triangle. And because it's isosceles, the base angles should be congruent. So then I use some arithmetic, and I know that they all have to add up to 180, and I know that the vertex angle is 60, so I take that away, and 180 minus 60 is going to give me 120. And so now I have 120 degrees left, and they have to be the same. So I divide that by 2, and I get 60. So now that means that all of the angles are 60. So now not only is it isosceles, it's actually equilateral. So for the measurement of angle Y, we're going to say that that's 60 degrees. And then it's asking for segment YZ. Since these are 8 and this is an equilateral triangle, then that's going to equal 8 inches as well. And there you go. So now you'll use the second diagram to determine the measurement of angle M and the segment PN. Alrighty then. So Now we're going to go to example 3. And this is probably our last example. It's a very short video today. It says find the value of each variable. And again, we're going to use some of the stuff that we just talked about earlier. This is, again, an isosceles triangle. At best, right now, at least we know that much. And we know that because these two are marked congruent. So if this is 3 inches, then AC is also 3 inches. I'm going to go ahead and add that to my diagram. But then also, it's equilateral. So beyond being isosceles, it's actually equilateral. And I know that because these two angles are both marked 2x, which means they're the same. And if these are the base angles the same, then these two legs should also be congruent. So if all 3 legs are congruent, now we have an equilateral triangle, which automatically makes it an isosceles triangle. Since we know that in an equilateral triangle, all of the angles have to be 60, then we know that 2x equals 60, and therefore we divide by 2, and then we get that x equals 30. Okay, so that's the first variable there. And then, again, because it's equilateral and these two are 3 inches, then this segment has to be 3 inches. So we do 4y minus 5 equals 3 inches. And then we're going to add 5. So 4y equals 8 inches, divide by 4, and we get that y equals 2 inches, or well, it equals 2. Okay, so y equals 2 and x equals 30. And so we have found the value of the variables. And so now you can try the do-it-yourself question, which is over here on the right of the board. And then once you have done that, you will have completed your notes for this lesson. And I will see you in class, and thank you for watching.